To start off this presentation, the feedback controller design is a necessary aspect of controller design to accurately track this DC motor system at the desired speeds while limiting the real-world disturbances with the inclusion of proportional, integral, and derivative gains. This report will cover the open and closed loop behavior of a DC motor system, as well as its implementation to the Arduino coding system. The original transfer function in Project 1 was first depicted as a second-order system. Through analysis and derivation, this model can be displayed as a first-order system due to the oscillatory motion within the motor being negligible, therefore eliminating the need for a PID controller and making it a PI controller. I'll now give it over to Luke to talk about the open and closed loop system and the root locus part.
Substituting the DC gain and time constant found in Project 1 into the equation, the open loop transfer function was found to be g of s equals 31.2375 over 0.159s plus 1. Time constant tau equals 0.159, which means it takes 160 milliseconds to reach 63.2% of the steady state value. The open loop function has no zeros, since no value of s makes the numerator equal to 0. There is a pole at s equals negative 6.29 radians per second, found by setting the denominator equal to 0 and solving for this. Since there is only one pole which lies on the negative real axis, the open loop system is inherently stable and does not oscillate. This can be seen by observing the open loop response over time graph to the right, which shows the system RPM over time after turning the motor on. The open loop output can be found by multiplying the transfer function by the step magnitude in the cross domain as seen in the second equation. The open loop response exhibits characteristic behavior of a first-order system. The response rises smoothly with zero overshoot. The rise time, which is the time it takes for the system to rise from 10% to 90% of the steady state value, was found to be 0.349 seconds. The closed-loop transfer function was then also found by using a unity feedback. Closed-loop transfer function was found to be 31.2375 over 0.159 seconds plus 32.2375. Closed-loop transfer function also has no zeros, and it has a pole at s equals negative 202.7 radians per second. This results in a new time constant of 4.93 milliseconds. The rising time was found to be 10.8 milliseconds and the settling time 24.6 milliseconds. Closed-loop system is therefore much faster than the open-loop system when comparing time constants and rising times. The closed-loop DC gain is 0.9693, and with a reference input of 240 RPM, the steady-state value becomes 232.6 RPM. To find the step response, the transfer function was again multiplied by the step input, and the responses in the frequency and time domain can be seen in the second and third equations. The response of the closed-loop system over time is graphed on the right. The root locus was used to examine constant loop poles of the closed loop poles of the system in the complex S-plane as the gain k varies from 0 to infinity. The closed-loop characteristic equation is defined as 1 plus k times g of s equals 0, which when rearranged and plugged in for results in the equation on the slide. Using the root locus method, it can be seen that when k equals 0, the pole begins at minus 6.29 radians per second, which, as we saw before, corresponds with the open loop system. As the gain increases, the pole then moves along the negative real axis towards negative infinity. It never becomes positive and it never leaves the real axis. This means that for any gain, the system will always be stable and will have no oscillatory behavior. It also means that the damping ratio remains constant at 1 and the overshoot will remain 0 for any positive gain. Since there are no poles at s equals 0 in the characteristic equation, the system type is a type 0. Since it is a type 0, there will always be a steady state error. This means that the proportional controller will not be enough to eliminate the error, and thus we need either a PI or a PID controller.
PID controller was designed and optimized for the system. So the goal for this PID controller was designed was to refine the closed loop step response. To optimize this response, the main objective was to eliminate the steady state error that was introduced by the unity feedback earlier, while also minimizing the settling and rise time. The following transfer function was found in the top right, which is of the form C of S equals Kp plus Ki over S plus Kd times S. Kd was designed to be 0 because there was no oscillatory behavior that needed damping from the open and closed loop responses. Kp, which is the proportional term, was set to 2 to slightly improve the speed of the response. The integral term Ki was set to 15 to effectively eliminate the steady state error that was observed in the closed loop response. So when multiplying this with the plant transfer function, the following was found, and then therefore our final closed loop transfer function is this. So as our results, we have a table that compares the open loop, closed loop, and the PID, rise time, settling time, overshoot percentage, and peak value. So as the results show, the rise and settling times have slightly improved from the closed loop times. The proportional gain of 2 was kept low to avoid introducing significant oscillation and overshoot. The steady state error introduced in the closed loop section has been fixed, and the system now settles at 240 RPM with less than 0.1% overshoot.
Implementation of the Arduino came from first getting the values of the proportional, integral, and derivative gains that both Robert and Luke worked hard to derive and obtain for me to use. The circuit setup that was used within this experiment and project was the same as Project 1, as seen in the figures on the screen and on the presentation slide. So that made it easier to then create a whole new code that implements these new gain values and operates the motor at 80% RPM capacity, which the motor that we used was 300 rotations per minute to get a steady state of 240 rotations per minute whenever the code ran. The samples times were at 100 milliseconds, and we ran this in Arduino until steady state was achieved, and it was oscillating between 240 RPM within plus minus of 2 uncertainty. Then, after obtaining that data, loading it in MATLAB and creating both a MATLAB code that plots the Arduino data and also has plots for simulated computed MATLAB data, as shown in the figure on this slide. The Arduino shows close agreement to the simulated data, with disturbances along that line after steady state has been achieved just due to small encoder responses and disturbances that happen within the motor itself that we cannot contain with the gain values and the PID controller design. The reason why MATLAB contains a straight line is because MATLAB assumes ideal conditions. Therefore, there's not going to be any oscillatory behavior, and it is able to look much cleaner than the actual simulated data, which takes into account real-world things, such as the encoder being slightly off, causing the oscillatory behavior, but still remaining at that 240 RPM threshold.
In conclusion, the unity feedback closed loop response revealed a significant steady state error, which enhanced the need for a PI controller with Kp equals 2 and Ki equaling 15. The resulting controller successfully eliminated the steady state error, while also achieving a settling time of 0.2909 seconds and a near zero overshoot of 0.07%, while also settling at a desired 240 RPM. The experimental Arduino implementation confirmed a strong agreement between the simulated and measured responses, as the motor reached the target speed of 240 RPM. Overall, the identified transfer function proved to be an accurate model of the physical system, and the PI controller demonstrated its effective performance.